Hello to all my dear learners. I am Aishwarya Sharma, Civil Wallah, welcoming you all on this platform Gate Wallah. So we are going to see one short series in English language, and today the topic is bond. The last topic which we covered was shear, and today we have to talk on bond. Okay. So dear, it is I think the 6th session today, and I am your friend Aishwarya who is going to lead this topic. Okay. Now, my dear friends, all these are the agendas of today's session. We are going to see what is bond, how many types of bond stress exist, what is the development length, and what are the important IS code recommendations in bond, because those are very much required from your exam point of view. And after that we will be seeing 2 to 3 numericals. Numericals are quite easy from this chapter. Okay, only 1 or 2 concepts are being asked. Okay, so let's start the session, my dear friends. So if you will ask me what is bond, then I will tell bond is basically which is going to bind steel and concrete. If we want to keep steel and concrete act together, then bond we literally need. So it describes the mean by which a relative movement between steel and concrete is prevented. Okay, if there would be perfect bond between the steel and concrete, between the steel and surrounding concrete, then we can say that no slippage is there and there is a perfect bond between steel and concrete. My dear friends, whatever amount of steel we are going to give to concrete, that would be effective only when there is a perfect bond between steel and concrete. For example, if I have provided some amount of steel and this is the surrounding concrete, doesn't matter how much good quantity of steel you have taken, how well you have conducted your design, but if this slippage occurs, if this bond breaks, then there is no use of this steel, because it will not be effective anymore. Okay, so what I want to say in short, if we want to keep our structure a perfect, if we want to make steel utilization up to 100%, then there must be strain compatibility. There must be no slippage between steel and concrete. Then only we can say that yes, a perfect bond exists between steel and concrete. So we will be watching today that what all are the means by which we can understand this bond, bond strength, bond stress, okay, and how we can make sure that we have provided the sufficient amount of bond length and all. Okay. Okay, my dear friend, somebody might be thinking that what is the strain compatibility? Strain compatibility is like that when steel is surrounded by concrete, and if I am going to apply some strain over there, may it be compressive or tensile. So by the amount with which steel would be extending, if with the same amount concrete is also extending, then we can say that there is a perfect compatibility between steel and surrounding concrete. Okay, so you can see that it is bond only if there is a perfect strain compatibility, means the forces can be transferred from steel to surrounding concrete. If it is this bond only which is responsible for the transfer of axial force from reinforcing bar to the surrounding concrete, and obviously if this bond will be inadequate, then slippage will occur and there will be no use of providing steel, isn't it? Okay, actually the stress which is acting on the outer interface of steel to the surrounding concrete is called bond stress. Obviously it is action. So whatever stress we do have here, so between this contact area which is circumferential here, so there is some stresses, okay, and these stresses would be called as bond stresses because they are originated due to this bond action. If we want to make our design safe, then we have to make sure that these bond stresses are less than the design bond strength. Okay, then only we can say that we are safe here. So that is this is the reason why understanding of bond stress is very important. Okay, bond stress also helps in keeping bond between reinforcement and concrete together, obviously, and bond stress resists any force that tries to pull out the rod from the concrete. Rod means steel bars. Okay, so it is going to resist that. If you will ask me that what are the mechanism by which bond stress develop, then total 3 actions are there: adhesive resistance, frictional resistance and mechanical resistance. So bond stress will be developed due to these 3, and adhesive resistance is basically produced by the chemical gum released by the concrete during the setting of concrete, and frictional resistance developed due to the frictional action, due to the normal forces, due to that only the frictional resistance developed there, and mechanical resistance developed due to the interlocking of you can say concrete particles. Okay, due to the interlocking of particles, and mechanical resistance you can observe in corrugated bar, or you can say in HYSD bar. So total bond stress is due to 3 reasons. First, adhesive resistance produced due to the chemical gum produced during setting of concrete. Second, frictional resistance, name itself is sufficient due to the frictional action, and third one is mechanical resistance, and third one is dear mechanical resistance. Mechanical resistance is applicable only in corrugated bar, or you can say in HYSD bar. Is it clear? Okay. Now let me tell you one more thing here. Let me tell you one more thing, that out of these 3 resistance, strongest is mechanical resistance, frictional resistance is obviously intermediate, and adhesive resistance is the weakest one. Means if you are going to pull your bar, then it is the adhesive resistance which is going to break first, after that frictional, and then mechanical. But yes, mechanical resistances are available only if bar is HYSD, or it may have some corrugations. I hope you understand the corrugations. Corrugations are like this. Okay, so due to the interlocking of this concrete material within the corrugations of bars, you are getting the mechanical resistance, isn't it? Okay, and now how many types of bond stress exist here? Total, my dear friends, there are 2 types of bond stress. First one is flexural bond stress, which is developed due to the indirect action, means bending is there, due to bending tension is there in the steel bars, and due to the difference of tensile forces at different section, there is some unbalanced force, unbalanced tensile force, and that unbalanced tensile force is trying to pull the bar, and that pulling is to be resisted by the gripping between steel and concrete, and the developed value of stresses in this mechanism is known as flexural bond stress. Second type of bond stress is your anchorage bond stress, which is working in the direct compression, or you can say in direct tension. So whenever you are going to pull your bar directly from your concrete block, then whatever amount of stresses are developed, those are known as anchorage bond stress. So in direct tension compression you can say anchorage, and in indirect tension compression you can say it is flexural bond stress. Okay, if we want to make our design safe, then we have to equate both of these, and accordingly we have to develop the relation that we will be watching in the development length expression. Okay, so first one, as I told you, flexural bond stress, also it is denoted by tau BF. Second one is known as anchorage bond stress, also it is denoted by tau BD. Okay, so flexural bond stress, you can say that here the change in bar force along its length due to the variation in bending moment in its length. Okay, this type of bond stress is known as the flexural bond stress. What is happening, my dear friend? Just listen here. If suppose if this is my beam, okay, and if this is beam, and let's suppose there is some bar. If there is some bar, let's suppose like this. So what is happening on the application of load? On the application of load, this bar is going to deform. this bar is going to deform. Maybe it is deforming like this. Okay, so this reinforcement will also be elongated this time. This is the extended reinforcement. Okay, this pink one is the extended reinforcement. And what is happening? Due to the difference of forces here, like you can see here, this is your section 1,1, this is your section 2,2, and again let's suppose these both sections are separated by a distance dx. Then what would happen? This is 1,1, this is section 2,2, and here would be some c, and then here would be c plus dc, and similarly here would be some t, and here would be t plus dt. These are separated by a distance dx, and this is known as jd. This is known as jd. Okay, so if moment acting here is m, then here it would be m plus dm. You can see that due to this dm, due to this additional moment, some additional forces would be generated because lever arm is same. If bending moment is increasing here or decreasing here, it is changing here, it is only due to this plus dm or minus dm component. So due to this plus dm, plus dt or plus dc component is also coming here. So if you are seeing here, here the tension force is T, and here is different than that. If T plus dt is greater than T, then bar will try to go in the right hand side. So in order to block that motion, that slippage, what we need to do here? We need to resist it with the mean of some bond stress, and that bond stress developed here is flexural bond stress, because the difference of tensile forces is occurring due to the different value of bending moment on these corresponding two sections. I hope you are getting this concept. So what is flexural bond stress? So flexural bond stress is something which is originating due to the variation of bending moment. What is happening when bending moment is varying? Due to that, the tensile forces are also changing, and due to the difference of this tensile forces, there is a resultant moment on any one hand side. So in order to prevent that resultant movement, so you need to develop some stress, and that is known as the flexural bond stress. I hope it is clear to you guys. And if you will see that this dt, I hope you remember my last lecture. So you know this dt was the force which is also responsible for the shear for any point between the neutral axis and CG of the tensile reinforcement, and similarly this time again this dt is responsible for the bond action. So let me show you one slide from my previous lecture, that what we did on Friday. Okay, this I have simply taken from the last lecture. Okay, I hope you are watching this lecture after that lecture. So this is the unbalanced force, this is the unbalanced force, and this unbalanced force which was coming dm by jd is the force which is responsible for shear. Also again this dt is responsible for the bond. So this dt also responsible for bond stress, because if this dt would not have been there, then no tendency of slipping. So if no action is there, then no reaction is required, then no reaction is required. So my dear friend, one thing is sure, that this dt is dm over jd, it is the unbalanced force. Okay, and this unbalanced force, due to this unbalanced force, your bond stress is coming into the picture. And why I am calling it flexural bond stress? Because this dt is originated due to the difference of bending moment, you can see here, isn't it? Now what will happen? If, let me show you this with the help of this diagram. Suppose if this is section 1,1 and section 2,2. I am trying to show you it in the 3D manner. I am trying to show you in the 3D manner. Okay. Okay. So let's suppose there are several bars. Let's suppose there are several bars. 1, 2, 3. Okay. If this is dx, this is b, width of the section. This side is section 1 and this side is section 2 2. Let's suppose here there is a net force T plus dt, and let's suppose here there is a net force T. So unbalanced force is dt, and that dt is causing stress over the circumference of these bars. Okay, let's suppose I am showing these bars like this in 2D. If I am showing them in 2D, so the things are like this. If these are my bars, and on one side there is T plus dt, and another side if it is T, then the net tendency is here of dt, then net tendency is here of dt, and this net tendency will be resisted by this. Okay, so don't think I have shown you only one bar, so I will take summation while I am calculating its area. So if this is tau bf, now you can see if we are going to apply the equilibrium of forces, because you know in reality if we want to be safe, then it has to be in static equilibrium. So for that scenario, if we are going to make summation of fx is equal to 0, if this is x direction, then minus t plus dt minus tau bf into summation of O. Summation of O is the sum of perimeter. If it is a one bar, then pi into phi. Okay, if it is all bars, then pi phi of all bars into multiplied by n. So into tau bf into summation of O. And what about this distance? This distance is simply this one, dx only. This distance is, you can see, dx only. This is equal to 0. Now this t and this t will be cancelled, and from here you can get the value dt is equal to tau bf into summation of O into dx. Okay, so let me again call it equation number 2, and the one which we have seen on earlier lecture, let me call it equation number 1. If I am going to equate this equation number 1 and that equation number 2, okay, so what we are going to get here, we will be getting from 1 and 2, dt was from 1 dm by jd, from 2 dt is equal to how much? It is equal to tau bf into summation of O into dx, tau bf into summation of O into dx. If I want to calculate the value of tau bf, it is equal to dm over summation of O jd into dx, and again I can write it here that dm by dx is nothing but the shear force. So if this is shear force, then my dear friends, tau bf is again a function of shear force upon summation of O into j into d. So this is the developed value of stress in flexure due to the difference of bending moment. Or we can say, if we are knowing the shear force, due to that shear force, because rate of change of bending moment is shear force. So if we are able to calculate the shear force, then tau bf can be written as V divided by summation of O into jd. Okay, and from here one common aptitude things comes into the mind. My dear friends, many a times it also have been asked in previous years of GATE and sometimes in SSC JEE that or ESC prelims as well, that how we can control the value of tau bf. Obviously we cannot reduce the value of shear force, because that is from design. Okay, JD also most of the time remains constant, or the difference between the JD, if we want to increase the value of JD, it is not at all easily feasible, because changing C and T resultant lever arm is quite difficult. Okay, for that you need to decrease the area of steel and all, so you cannot, you are not allowed to do that. So what only things comes left is summation of O. How we can increase the summation of O? If anyhow we manage to increase this value of summation O, then tau BF value can be reduced, because here you can see if the denominator is increasing, then overall tau BF value will be decreasing, then overall tau BF value will be increasing, isn't it? So if amount of steel is to be kept constant, and for that same amount of steel, okay, same amount of steel, you are replacing that steel with smaller diameter bars, obviously you would be needing more number of bars. If you are reducing the diameter of the bars, in order to compensate the area, in order to keep the area constant, you would be needing more number of smaller diameter bars. So for the same area, if smaller diameter bars are used, then its number will be increased and its summation of O will also increased. So by this you can control the value of flexural bond stress. Okay, so it is a very important point. If we want to control the value of flexural bond stress, then what is the suggestion? We can replace bigger diameter bars with smaller diameter bars for a same area, for a constant area. By doing this, circumference value increases, and due to this bond stress value decreases, isn't it? So it is a very important point here. The next is anchorage bond stress. So it is actually the stress induced in the bar due to the anchorage. Okay, and it arises when bar carry a certain axial force, and this axial force is to be transferred from these to the surrounding concrete. It's very simple. Okay, it is the direct action, direct pulling or direct pushing is your anchorage bond stress. Okay, if you want me to explain this, then what we can do here, it's just like, suppose if we have a block here, like this, and over this block if there is some bar, let's say like this. Okay, and if this bar is going to pull with some amount force T, this T would be equal to, you know how much it is? It is 0.87 Fy into AS T, like this, 0.87 Fy into AST. And how it is going to resist? It is going to resist by this. This is direct bond stress, so it is tau BD, and let's suppose it is the length of embedment, let me call it L. Okay, so you know this, if phi is the diameter of this bar, then in order to maintain the horizontal equilibrium, you can say that minus tau BD into L into summation of O is equal to 0.87 Fy into n times of pi by 4 into phi square, if n is the number of bars. Okay, if n is the number of bars. And what is summation of O? And what is summation of O? Summation of O would be, I am simply using the equal to sign, minus this plus this is equal to 0, so this would be equal to that. So if tau BD L n into pi into phi is there, then it is equal to 0.87 Fy, okay, n pi by 4 into phi square. So 1 phi cancel, 1 pi cancel, so n and L will also cancel. So from here you can say that L is equal to, or tau BD is equal to 0.87 Fy phi over 4L. My dear friend, but here the problem comes in the reverse manner. The value of tau BD is known to you. The value of tau BD is given in the code. Okay, if I am going to show you this value, so you can see here that it is given in this code, and based on the grade of concrete, you can see here that values have been given. But there are two things which we need to keep in our mind here. Okay. For example, if I want to calculate that safe length for which failure in bond must not happen, even if breaking of steel can happen. So what would be that length? So that length would be LD, and this would be equal to how much? It is 0.87 Fy phi upon 4 tau BD. Okay, are you getting it or not? So at this tau BD, okay, this is the value of LD and this is the value of length. If we are going to provide this much of embedment, then what would happen? Pulling of bar will not be there. Okay, or you can say we have originated this scenario for equality, so you can say pulling and failure of bar in tension would happen simultaneously. So as long as the length of embedment is greater than, even if it is slightly greater than this amount, then your bar will not fail in tension, bond. Then your bar will not fail in bond. It may fail in tension, but it will not fail in bond. So if we want to make our bond stronger, then the minimum length of embedment must be equal to this 0.87 Fy phi upon 4 tau BD. Okay, it is not that clear. 0.87 Fy phi upon 4 tau BD. Okay, so this tau BD value is given in the code, the figure which I have shown you just now. Okay, and this LD value have been developed based on the criticality. You know that this tension is more dangerous than that tension which originated in flexor case. There the tension was indirect, but this is the direct action. So this this length is more critical, and whenever we want to check the safety, we have to make benchmark to the more critical scenario. So whenever we want to make sure that my structure is safe in bond or not, then I need to calculate this LD, and if the available length of embedment is greater than this, then we will be saying yes, our design is safe. If our available length of embedment is less than this, then we will be saying no, okay, so it might fail in bond, my structure can fail in bond. Another thing is this, there are some relaxation. You know, this tau BD value which you can see here, it is for plain bars and for tension. There can be instances when in place of plain bar there are HYSD bar. So in that case, sir, what to do? Are we going to provide the same development length or same anchorage length? Because if there would be HYSD bars, then there are corrugations, and due to corrugations we would be getting some more relaxation. So why to keep the value of tau BD same? Another thing, if in place of tension, sometimes there are circumstances when compression is there, so it should be more safe there, because in compression along with the bond and bearings are also coming into the picture. Okay, so IS code has given this bar, these values for plain bars as well as for tension. But if instead of plain bar, if we are going to use HYSD bars, then these values are to be increased by 60%. And similarly, if in place of this tension, if compression is acting, then again we can increase the value by 25%. And if both are acting, then first of all we have to increase 60, then 25, so ultimately the value is going to be double. Okay, 60% of 100 is 160 and 25% of 160 is 40, so value is 200. So simply if HYSD bar and compression, both the things are acting, in that case we can simply double our tau BD value. So the tau BD expression which you are seeing here, which you are watching here, is for plain bar in tension, but in our case most of the time the scenario is HYSD bar. So then this tau BD would get multiplied by with 1.6, 60% increment. If compression is there with mild steel only, then this value will increase by 25%, okay, 1.25. If both are acting, then 1.6 into 1.25 is nothing but it is 2 only, isn't it? Okay dear. And yes, what all are the important provisions of IS code for this tau BD? As I told you that tau BD for deformed bars is to be increased by 60%. Why we have to increase it by 60%? Because of the deformed bars, my dear friend, the actual contact area of the bar with concrete is much more than the contact area based on the nominal diameter of the plain bar. It is corrugation, the actual contact area of concrete. Okay, it is not just plain like this, it is like this. So if you are watching this contact area, so it is more. How much it has taken more? As per codal provisions, it has taken 60% more. So we are going to increase the value of tau BD by 60%. And for bars in compression, this value is to be increased by 25%, because now end bearing is also there, so it is going to give you some additional support, because the end bearing of the bar helps in resisting compression. Also the possibility of cracking concrete is very less, almost nil in compression. Okay, so these two are the provisions which have been given on tau BD. Okay, so this is the first aspect which is very frequently asked in your GATE, ESC prelims and SSC JEE. Okay, now second thing is from design point of view, and that is basically the development length. Development length, actually whenever we are going to compare our bond stress and in flexure and bond stress in anchorage, in that scenario we will get the value of development length. And in development length we will be seeing, we are going to calculate one length from the anchorage because that is critical, and second we are going to calculate from the flexural. Okay, and on that comparison we can deduce a general expression. Okay, so what is happening in development length? You know what is tau BF? Tau BF is V over summation of O into JD. Okay, you also know what is tau BF as per anchorage. Just now we have seen that 0.87 Fy AST is equal to how much? That was equal to tau BD into summation of O into, let's suppose it is LD only. For this scenario it is LD. Okay, later on we can take it LD for this critical conditions. So make it LD everywhere because we have equalized it. Okay, and from here tau BD can be written as 0.87 Fy AST upon summation of O into LD. Now my dear friend, if you are going to equate both this scenario, okay, this is, you can say, the action. Tau BD is the, you can say, strength of concrete, it is a reaction. So for a critical condition we have to make sure that action and reaction are matching. Okay, and for safety this action should be less than reaction. This action should be less than reaction. If we are calculating it for the critical condition, then we can say here that V over summation of O into JD is equal to 0.87 Fy into AST upon summation of O into LD. Okay, and if we are solving this inequality, then or equal to only, then LD is equal to 0.87 Fy AST into JD, cancel it, upon V, and for critical condition LD is equal to 0.87 Fy AST is the tensile force, it is the lever arm, so I can call it M1, it is V. So this is the scenario. And for safety, my dear friend, if less than sign would have, if I have used here, then LD should be less than M1 over V. LD should be less than L1 over E. Okay, so this is the availability, this is the requirement. So if we want to keep ourselves safe in bond, then the availability must be greater than requirement. Requirement we will always be calculating as per the worst condition, as per the critical condition, and this requirement LD is 0.87 Fy phi upon 4 tau BD, and M1 over V is the availability. It is as per the actual bond stress. Okay, you can say, isn't it? So here, my dear friends, I would like to conclude it with some important codal recommendations. Okay, so if this value is LD is less than equal to M1 over V, then what all are the important codal provisions? First is LD is always less than equal to M1 over V. Okay. Okay, it means the development length is less than equal to the embedded length of the bar. The code has given the additional value of L0. Code is saying that if we are using plain, I think it is not that visible. Okay, I am reading for you. I don't know how I selected this font. Okay, yeah, the code has given additional value of L0, and this L0 is also known as anchorage length. So here the LD must be less than equal to M1 over V plus L0. M1 over V plus L0. This L0 is the anchorage length, which is the sum of anchorage beyond the center of the support and the equivalent anchorage value of any hook or mechanical anchorage at simply support. So this L0 you are going to measure from the center of the support. Okay, first of all, this L0 is required only in plain bar. In HYSD or in corrugated bar, requirement of L0 is only when it is needed actually. Suppose if M1 over V is not sufficient itself, or suppose if the value of M1 over V is less than LD, it means the requirement is more and availability is less. In that case, code is saying that you can add some value of L0, but L0 value addition is compulsory. It is compulsory for plain bars. In HYSD bars, L0 is required only if needed. Only if needed. Okay, and L0 we are going to provide beyond the center of the support. Okay, so like if this is my simply supported beam, if this is my simply supported beam, then we are going to measure L0 beyond this. It may be like this, it may be like this. Okay, it may be like any shape. Okay, basically three shapes are used: 45-degree bend, 90-degree bend, and 180-degree hook. Okay, and for each 45-degree we are going to increase its length by 4 phi. For example, for 45-degree bend, LD is 4 phi. For 90-degree bend, LD is 8 phi, and for 180-degree hook, LD is 16 phi. Okay, so that is the case. And one more thing is there: when my slab is confined by some compressive resistance, like in the case of simply supported beam. So what is actually happening? Whenever my support is confined by some compressive resistance, then the gripping is increased. So that increased value of gripping is justified by IS code, and IS code recommended that increase the availability of the development length. Instead of M1 over V, code is saying increase it 30%. Why it is 30? It is experimental. But why it should be increased during compressive confinement? For that I can provide you the logic. Okay, whenever the supports are confined by some compressive reaction, then the grip is increased, and now the pull out is more difficult. Due to that, the embedded length is considered more, and code has taken the 30%. Okay, let me read all the codal provisions for you one by one. So first is selection. Again, very L naught is limited to effective depth of member and it is equal to D means effective depth or 12.5 whichever is greater. Okay, you know at point of inflection bending moment is 0. If bending moment is 0 then the whole and sole thing will depend upon L naught. So for such critical sections in point of inflection L naught is limited to D or 12.5, phi is the diameter of the bar whichever is greater, D is the effective depth. Next, bond stress is maximum at a section where shear force is large. We have seen that in tau BF it is this value was directly depending upon shear force V. Okay, next, check for bond stress, check for flexural bond stress is necessary at a section when bending moment is 0 and shear force is maximum. So two sections are critical when shear force is maximum and bending moment is 0. What could be this location? At simple support, my dear friends, shear force is maximum and bending moment is 0. And at the point of contraflexor, bending moment is 0. So at both these locations, bending moment value is going to be equal to 0. Are you getting it or not? Okay. So some more IS code provisions. It is basically for bundling of bars. So bundled bars, here the development length of each bar of bundled bar shall be increased by, if 2 bars are there then 10%. Why it is increasing or decreasing? Why it is increasing? Because due to the bundling there is a change in the surface area. If 3 bars are in contact then 20%, if 4 bars in contact then it is 33%, isn't it? Next is anchorage. So as I told you, in case of hooks and bends, when the required straight development length cannot be provided due to the limited space at the end of the beam, in that case standard hooks and bends are provided to fulfill the development length. For U type hook, as I told you, it is 16 phi. For L type or 90-degree bend, it is 8 phi, and for 45-degree bend, it is 4 phi. Okay. So whatever is satisfying, you can use that. Okay. But most efficient is obviously U type hook, because here the incremental length is very high, isn't it? So my dear friend, now one important note, as I also explained to you this earlier, that deformed bars may be used without end anchorage beyond provided that the development length requirement is satisfied. If development length requirement is satisfied, means if LD is less than M1 over V, in that case no need to provide L naught. Okay, but whenever we are designing, we are checking the bond in plain bar, in that case we need to provide L naught. In fact, not only L naught, but that L naught must be in the form of hook, 180-degree hook, isn't it? So that is written here. Hook should normally be provided for plain bar in tension, isn't it? Okay, that is also quite logical, because we cannot rely much on the plain bar. So we need to give a proper bond by turning our main bars in the form of hooks. Now some small numericals, let us see. So first numerical is that what is the value of tau BD with the deformed bars? First for tension with M20, and second is for compression with M20. What is the value of tau BD for M20? I have shown you there. The value of tau BD here, it is 1.2. Value of tau BD is 1.2 MPa or Newton per mm square. Now if M20 for a tau BD value is if it is M20, then in that case how to find it? Tau BD is 1.2. If it is a bars in tension, okay, for tension with M20, for deformed bar, the value is to be increased by 60%. So revised value of tau BD would be 1.2 into 1.6. Okay, I think it is 1.96, you can check. And another is, if bars are in compression, then tau BD value would be, original value is 1.2, first HYSD correction, then so this value would be 2.4. check out this value, and this is 2.4 because this value is going to be doubled. Okay, next question. In LSM, the permissible bond stress in case of deformed bars is more than in plain bar by. This is a joke. Okay. So I told you that it is a caudal provision. So it is to be increased by 60%. Had this been a case of compressive forces, then it would have been increased by 25%. Or if I am going to assemble both these cases, then value is 100%. Okay. 60% then 25% is 100%. And one more question we can see here, that as per the caudal provisions, M20 concrete and plain bar in tension, design bond stress is 1.2. Just now we have seen it is for M20 it is 1.2. Further, IS code is saying that design bond stress value to be increased by 60%. It is gate question, I think. Okay, for HYSD bar, okay, it is given, very honest question. Whatever are the clauses which we must be knowing, they are telling us that yes, it is to be increased by 60%. The stress in the HYSD reinforcing steel bar in tension is 360. Okay, so directly they have given you this stress. Okay, so 0.87 Fy instead of 0.87 Fy, it is given it is 360. Find the required development length for HYSD bars in terms of the diameter. Okay, so we can see that LD is 0.87 Fy phi upon tau BD. Here 0.87 Fy is directly given to you sigma s. Phi, what about phi? Okay, in terms of phi we have to give answer. Upon what about tau BD? Tau BD is 1.2 in normal scenario, now it is 1.6. So this would be 360 over 1.2 into 1.6 into 5. Okay, so let me calculate this only. So answer would be how much? It is 360 by 1.2 into 1.6. So it is how much it is coming? 4 will also come. It is 46.8755. It is 46.8755. Okay, and this 1.2 into 1.6 is 1.92. 1.92. Okay. So my dear friend, these all are the numericals, very easy numericals as I told you. Okay, so it is 46.8755. Okay, so I hope you understand what is bond. So I have covered all the important clauses as well as important derivations. So if question comes in from this portion, then it must be this LD, or it may be some caudal provisions. Okay, or it may be related to development length. Okay, so from these three area your questions in exam may come. Okay, so I will bring some more questions in other format, like in series like Abhyas or numerical series and all. Okay, and in fact I have taken a Abhyas series in Hindi language in Gate Wallah channel, Hindi channel, ME, XE and CE channel. So there you can find more number of problems. Okay, so thank you my dear friends, thanks a lot and take care, and day after tomorrow again we will be meeting with our next topic, which is torsion. So thank you very much.